Hello, everyone. This is Tuba Yavuz. I'm a faculty member at the University of Florida. I'm going to present a tutorial on detecting memory vulnerabilities in the components of system code using prompt. This is a joint work with my PhD student, Yihang. First, I'll provide some important information about our tool and the virtual machine image that we created. If you can download the virtual machine image, hopefully you can follow the hands-on activities in this tutorial. We will start with some background information on symbolic execution and the KLEE execution, symbolic execution engine on which prompt is built. I hope that during part 1, you can install virtual machine image so that you can get ready for part 2 and part 3, in which you can hopefully follow the examples and try them on your own. After the background information, we will provide some brief explanation of what our tool is about by explaining our approach on API model-guided symbolic execution. Then most of part 2 will be about some tutorial examples. These are pedagogical examples to introduce various features of prompt and its specification language PROSE. And then in part 3, we will talk about some real-world case studies and memory vulnerabilities that we could reproduce using prompt. We'll conclude with some acknowledgements and we'll get your questions. We have released prompt on GitHub, so you can find out the path to the GitHub repository on the slide. So there are some documentation on the GitHub page, such as the manual, a template for PROSE specifications for you to get started with. Most of them are commented out. You can just turn them on by removing the comments, and we have some tutorial examples under prompt examples directory. We have some benchmarks about the Linux device drivers and the Bluetooth protocol that we have used in our journal paper. And also we have a directory about the heartbleed vulnerability. We have created a virtual machine image for prompt, and you can download it from this Google Drive link. Both the username and the password is prompt. And if you don't have VirtualBox right now, you can go ahead and download it from this link and make sure to get the most recent version. And when you install this virtual machine, you will find out that the prompt source tree is under prompt directory, all capital. And we also built or installed actually prompt under this prompt builder in a separate directory. So if you can actually set the prompt environment variable to the path to the executable, which is called KLEE, and it's under the bin directory of the build directory, then I think it will be very easy for you to follow the examples, because we have provided a script run.sh for each example, and it will be very straightforward for you to run the examples. You can definitely open run.sh in an editor and learn more, but I think just to follow the examples in the tutorial, that's what you need to do. Make sure to set the prompt environment variable to the path of the executable. Okay, so let's get started with a background on symbolic execution and understand what this technique is all about, and also understand how the KLEE symbolic execution engine works in a nutshell. Then we will continue with topics on prompt. All right, so in this part, first we will briefly describe symbolic execution with a simple example, and then we will show how KLEE symbolic execution engine analyzes the simple example, what type of output it provides, and we will end this part with challenges of symbolic execution. Symbolic execution is a program analysis technique that has been introduced as a program testing technique by James King in 1976. As SMT solvers became efficient, symbolic execution became a more popular analysis technique. Symbolic execution interprets a program by propagating symbolic inputs according to the program logic. And there are basically two approaches to symbolic execution. Concolic execution and execution generation-based testing. Since prompt is based on the KLEE symbolic execution engine, and since it follows the EGT approach, our examples will be about that approach. So here's a simple example for us to understand how symbolic execution works. So let's assume that we have a function called getSign. It takes an integer variable and it returns an integer value. And if you look at the body of this function, it actually tests whether the provided value is 0, whether it is a negative value or a positive value. And so if we do concrete execution, we have to provide a concrete value for x, and then we'll get a single value as an output. If you do symbolic execution, on the other hand, then we're going to mark the input, which in this case is the variable x, as symbolic. And symbolic means it's unconstrained. We don't know what x is. So then we will start analyzing this code using symbolic execution. What that means is we're going to interpret each program statement keeping in mind that one or more of the variables may have symbolic values, and then we'll propagate the values of symbolic values through assignments. And for conditional statements, like in this if statement, we will create a symbolic constraint and use a SMT solver to check for the feasibility or satisfiability of the formula. This way, the symbolic execution engine finds out feasible paths in our program, and then it creates what you see on the left-hand side. So here, sim(x) corresponds to the symbolic value of x, and as it actually executes each individual instruction, it finds out that there are different possibilities, like this branch, if this if statement at L1 holds, and if it doesn't hold, or if it doesn't hold because we're returning. So if it doesn't hold, then we continue with L3, and then of course L4 and L6 would be considered. So this way we propagate the tests performed on the input variables and accumulate these constraints in what we called a path condition by conjuncting individual constraints. And at the end of the day, we get a symbolic execution tree. And each leaf node corresponds to a separate test case. You can think of these test cases as equivalence classes of inputs. So they do not give us immediately some concrete value. As you see, for instance, this says sim(x) smaller than 0, and that obviously corresponds to this branch that returns -1. But using an SMT solver, we can find a solution for this one, or get a model, and then it may, for instance, give us -2, and then we can use this -2 as a test input, and it will obviously cover L4 and L5. So similarly, we can find at least one test from each test case, and then hopefully achieve 100% instruction coverage and 100% branch coverage. Well, for this example, that's the case, but unfortunately, as our examples grow in complexity, code length, and so on, this is a really difficult goal to achieve. And symbolic execution, as we will talk about, known to have this path explosion problem, because as this tree grows, it may grow exponentially. In the worst case, symbolic execution can be used as a bounded analysis technique. So as we mentioned, we built prompt on top of the KLEE symbolic execution engine. KLEE is a very mature tool. It has been around more than 10 years, and it received various awards due to its success. It's open source, obviously, and it has really good documentation. And KLEE is built based on the LLVM IR. LLVM IR is part of the LLVM compiler framework. So if you compile your code with the Clang compiler, then you can generate LLVM IR. And this is what actually KLEE expects as the input. So you don't provide the source files to KLEE. You compile your code with Clang, generate the LLVM bitcode, and provide this as an input to KLEE. The same works for prompt as we build it on KLEE. So KLEE follows the EGT approach that I mentioned. So it's basically the tree that I showed you, tree of test cases and intermediate obvious stages. KLEE works on closed programs. And what that means is that to analyze a function like getSign, we have to first create a test driver and tell KLEE which of the input we want to mark as symbolic, and then call the function we want to analyze. Here is an example. So the one on the left-hand side, the small code that you see here, is my test driver. And first I have to include the KLEE header file because I'm going to call an API function from KLEE, which is KLEE make symbolic. Since my getSign function expects an integer value, first I declare it as symbolic by passing the address to KLEE make symbolic and providing size of A, and then providing a descriptor string. In this case, I just provide A. And then I pass this to getSign, and I should compile this code and provide the bit code. As you see, you can compile it with Clang. Make sure to provide the include directory for KLEE so that it can find the header file. And then by saying emit LLVM and compiling this with also the debug option, we will get getSign.bc. BC is standing for bitcode. And then I can pass this bitcode to KLEE. Of course, if you also provide right K queries, then it will generate these test cases. As you see, we have some files generated under the KLEE last directory. And we have here 3 tests generated as we discussed. The K-query files are, I think, the most useful, especially if you don't want to replay the tests, which you can with the K-test files. So if you open the K-query files and look at it, and which we'll do next, you will see that it describes the test case, the symbolic constraint about the input variables. So if you look at the contents of these K queries, the notation may look weird at first sight, but if you look at it, so you will see these read LSB, read least significant byte. So this is the size information. So this is the symbolic variable, we're reading its value from starting from 0. So in KLEE, every memory object is considered as an array of bytes. So it starts from byte 0. The width is 32 bits. And then we read this value. Now this value is equal to 0. So this is the constraint on one of the paths. If you remember, that was our leftmost leaf. Another one checks whether this is not 0 and it is signed less than, it is smaller than 0. And this one checks whether this one is not smaller than 0. And as you see, each one of those correspond to different if statements in our getSign function. So let's change this getSign function a little bit. We're going to now change variable x into an array of integers and introduce another parameter, y. Now, let's assume that the contents of array x are symbolic, and y will be marked symbolic. Okay, so here, instead of checking x, because it's no longer a primitive variable, now it's an array, we're actually going to use y as an index into this array x. We have the same code structure, it's just that our variables have changed a little bit. Now let's look at the symbolic execution tree. Now here we have to, since the very first instruction will be an array access operation. So first, KLEE will check whether the value of the symbolic y is greater than the size of array x or not. Okay, so this is important because in the case that it is greater than or equal to the size of array x, then obviously it means we have a memory out of bounds error, and KLEE will generate a path for that. So that's one of our test cases. If it is not, then it means y can be used as a valid index. And then we will see the same symbolic execution tree that we have seen before. It's very similar, meaning that we will check for this value being equal to 0 or not 0, and then whether it is smaller than 0 or not, and so on. So one benefit of symbolic execution or dynamic symbolic execution in general is that it can actually detect memory errors due to precise representation of memory objects. So the type of memory errors that can be detected by KLEE includes null pointer dereferencing, memory out of bounds, reads or writes, use after free, double free, and memory leaks with some modeling effort, especially if you want to reduce false positives. Now, symbolic execution has emerged as a white box automated testing technique, but as SMT solvers became efficient, it also became a tool or a technique for detecting memory and other types of vulnerabilities. It's also used for reverse engineering and model extraction. Unfortunately, one of the biggest challenges in symbolic execution is the path explosion problem, as we mentioned before. And so this may prevent one from finding very deep bugs. Another problem in symbolic execution is obviously we talked about using or developing a test driver to analyze a component. And this can actually be very difficult for complex systems because such environment initialization requires a good understanding of the API, which is a big challenge on its own. So in part 2, We're going to present our approach on API model-guided symbolic execution and the tool we developed to implement this approach. Our goal is to be able to deal with complex system code using symbolic execution. So we will first introduce our motivation and compare our approach with existing approaches. Then we will give an overview of prompt, how it works. And we will introduce this input language called PROSE. And most of the time in this part will be spent on hands-on activity involving the tutorial examples that we have prepared. So as we mentioned, to analyze complex systems, one needs to have a very good understanding of the application programming interface, or the API. This is needed, for instance, if you need to prepare a test driver to understand how to provide a precise context for the components we want to analyze. Obviously, analyzing components is important. So rather than analyze a huge part of the system, we want to focus on components at a time. But to achieve precision, we need to provide a good context. Now, there are actually techniques that try to automatically learn the behavior of APIs. Unfortunately, they are not much mature yet. So there are these techniques like automated synthesis and machine learning, and they have their own challenges. For instance, in automated synthesis, since the state space is too huge, they have to guide the search using some syntax, like a grammar or some input-output samples. It's really difficult to get input-output samples for system code. So, and machine learning has this problem of a big semantic gap between semantic representations of programs and what is used by the learning algorithms. So it is ideal to be able to analyze a component within a precise environment description. And there are actually such techniques. For instance, KLEE implements under constraint symbolic execution, and it uses the well-known lazy initialization technique. So in lazy initialization, let's say that we have a complex data structure, such as a linked list that has maybe some primitive type fields in a struct type, but also some pointer types. So let's say that you have a utility function that analyzes or works on a linked list. So if you want to analyze that function, so what type of a linked list should you create first to analyze that function? How many nodes should it have? 1 node, 2 nodes? Or what could be the structure of the linked list? Maybe it is not a correctly implemented linked list, and so on. So the lazy initialization approach tackles this problem by creating such dynamic data structures as needed. As needed means we start with an abstract node, let's say, and then as we interpret the code symbolically, and if there is a reference to one of the fields, the pointer field, then that pointer field gets initialized at that point, not before. So that's why it's called lazy. So this way, the data structure gets expanded as needed. So yes, so this approach has been implemented in KLEE, but KLEE is not open source. So when we started doing this work, developing prompt, our initial goal was just to implement KLEE, and we thought that would be good enough. But later we realized that we needed some modeling to support lazy initialization or under constraint symbolic execution. So there's actually some modeling in KLEE. The models actually get weaved into the source code of the component. And also the goal of modeling is more about filtering out false positives. In prompt, we realized that we want to minimize changing the underlying code because it may not be so easy to compile code. For instance, compiling Linux kernel code is not an easy thing. Also, we wanted to provide API model guided lazy initialization so that we can have a better control over the path explosion problem and also for precision. So this diagram shows in a nutshell what prompt does. Again, it is implemented on top of the KLEE symbolic execution engine. And as input, it expects the component under analysis. And similar to KLEE, we expect the component under analysis in bitcode. And the other thing we expect is an API model, which is specified in the PROSE specification language. And then it can generate memory errors and other analysis results. So it can also generate some test cases. Test cases that are purely on the inputs can be used also for replay. But since we are doing component level analysis, some of the test cases that are produced by prompt may not be directly applied or used for replay. And our work is going to appear in the Journal of Automated Software Engineering. So if you work our tool, please cite our paper. So if you go back to the get sign function example, so let's describe how prompt kind of differs from KLEE. First of all, we do not need a test driver as we needed for KLEE. So if we have our component already compiled and we have the bitcode, we're almost good to go. We just need also a model. This kind of text file shows you a simple model. You have to include these main components: global settings, data models, function models, lifecycle model. If you just want to analyze your component without any modeling, then this is what it should like. You just need an entry point and mention the name of the function, the entry function, obviously. And then you will execute prompt by providing this model file with PROSE API model option. And you can still use write K queries, and you need to provide obviously the bitcode. And we kept a lot of things similar to KLEE. We wanted to leverage the fact that it's a mature tool. And similarly, we have this KLEE last directory get created. And under that, you can find test cases. So as you see, we again get 3 test cases generated, and we didn't need to write a test driver in which we had to manually, make them symbolic and pass it to the component under analysis. Although this is something very simple, right, for this very simple function. But as we start analyzing real-world systems and their components, writing a test driver again is really challenging. Whereas we can, hopefully, assuming that we have some understanding of that API, we can give some directions to prompt, and it will analyze the component according to the model. We will give more examples so this will become clear. So similar to KLEE, prompt generates these test cases, as you can see from the content of the kquery files. Maybe one difference is the naming. Since we didn't have a test driver, we didn't get to choose what name to give. So currently, prompt uses the function name and argument index and also, of course, the arg keyword to refer to function arguments. Of course, if they are symbolic, right? If they're not symbolic, they wouldn't have such a name. But in the future, actually, we're planning to let the user also define such symbolic names. So in summary, prompt performs under constraint symbolic execution under the guidance of an API model, and it doesn't need a test driver, which kind of simplifies the analysis. And hopefully the model that we come up with can help us achieve better scalability and precision. Prompt has been implemented on top of the KLEE symbolic execution engine. We had to change handling of memory access instructions like the load instructions, function calls, and return instructions. I don't want to go into details of the technical approach, which can be found in our article, but I'll be focusing more on how to apply prompt to first simple examples and then to real-world examples like Linux device drivers, some cryptographic libraries, and a Bluetooth protocol in the Linux kernel. So again, if you look at our GitHub repository, you can find a manual about prompt, which is mostly about PROSE features. To get started, I think you should use a template of PROSE model because it may take time to get used to the syntax. You just need to comment out what you need and of course include specific constraints, constants that are relevant for your model. We'll explain these 4 aspects of PROSE: global settings, data modeling, function modeling, and lifecycle rules. I think we have sufficiently rich tutorial examples for you to learn these features. Now we're ready to start the hands-on activity part of our tutorial. I'm hoping and assuming that you have installed the virtual machine image on your host computer. And so if you can open a terminal, you'll see that at the top directory, we have prompt source tree under all capital prompt. And you can find the tutorial examples, basically the pedagogical examples under the prompt examples directory. And you can find the real world examples that we'll be discussing, most of them under JSE benchmarks and the other one under case studies directory. We have installed and built prompt under prompt builder. So if you look at this directory, you will see, one of the subdirectories is the bin, which has the KLEE executable. Of course, this is prompt, but we actually kept most of the names same as in KLEE. Before starting executing the scripts that we prepared for you, please make sure to set this prompt environment variable to this executable path. If you forget to do this, when you run the script, you'll get an error. Then, of course, you can set it at that time in the worst case. Also, when you open a new terminal, you'll need to set this environment variable if you want to use the scripts. We are going to use this layout to organize our information when we go through the examples. So on the left side, top left side, you'll see the API model. We'll try to keep it as small as possible. And we will have our short snippet of code, the component that we'll be analyzing. And the code will be analyzed under the guidance of specified API model. So we'll provide both syntax and semantics through these examples. If you want to reproduce these examples and the results, you will need to follow these steps. As you know, we already told you to set the prompt environment variable. So if you have done this, then the next thing is to make sure that you're under the right directory. In general, the tutorial examples are under prompt examples. And depending on the type of the PROSE API specification, you will find the relevant directory, and we'll specify those as well. And the next thing to do is, for all tutorial examples, since the component bitcode is called foo.bc, by just running the script with foo.bc, you should be able to generate some results, and you can find the generated test cases under the KLEE last directory. On this section, prompt results section, we will tell you the number of test cases that will be generated, what to expect in terms of whether there will be an error generated at certain line or not. So all the test cases, as you have seen, will start with test and some number and some suffix, depending on whether they were successful or error paths, because error paths end with the error suffix. Okay, I think we're ready to start with our first set of examples about global settings. So as we mentioned, the main thing about prompt is that you can analyze a component without a test driver, because it actually performs lazy initialization of the arguments. An important decision in lazy initialization is to determine the size of the array that would be pointed by a pointer type argument. Now, the default value in prompt is 20 if the user doesn't specify anything, but we can control the setting in the global settings with the array size syntax, and you mentioned the size of the array here. So this applies to any lazy initialized pointer type. So in this case, argument A, excuse me, would have size 5. Therefore, using an index of size 4 shouldn't create any issues. Whereas when we use 5, obviously this is out of bounds, and so we should get an error at line L2. And so we have to go so we have to go to under prompt examples, go to global settings, array size. Then if you run the script, you'll be able to generate this error. So as you see, it's a memory error, so it has the suffix of PTR, pointer error. If you look at the content of this file, it will talk about the address, this memory error got manifested, and the line number. The other line number follows what is called an assembly.ll. Assembly.ll is the text representation of the LLVM bitcode, and later in an example I'll show you how to actually analyze or look at the LLVM bitcode and make sense of an error. And this is showing the that whenever you run the script, there will be an output directory generated, KLEE out, and then there will be a number. Each time you execute the run script, you will get a new number and a new directory with the unique number, actually. So, but KLEE last will always point to the very last directory that gets created, because it's a symbolic link. So a short notation is then to refer to KLEE last rather than KLEE out directories. All right. System code often include function pointers, And when we have function pointers, obviously an ideal thing to do is to initialize them with the relevant functions. But before seeing that one, first we'll see one way of handling function pointer fields, which is initializing all of them with null value. So we can do this with init function pointers to null on setting. So in this example, we have the bar field in struct A as a function pointer. And since we initialize this one, A1 is an A type and its bar field is initialized to null, this if statement will evaluate to false. So this assertion failure, because we provide 0 here, assertion failure will not be reached. So this is under global settings and then the directory init function pointers to null. So I hope you can try this on the VM and make sure you're in the right directory and then execute the script. And as you'll see, we will have this one test case get generated and we don't see any errors because the if statement evaluated to false due to our initialization. Now, system code often comes with functions with inline assembly. In this example, we have 3 functions, foo1, bar, and bar1 with inline assembly. What is inside the assembly block is not really important, but we have also some specific return value for these functions. Now, of course, one way of dealing with such functions is maybe use a lifter and lift assembly instructions to LLVM bitcode and analyze the bitcode that way. But still, prompt provides, ways of modeling such functions. So one thing we can do is we can tell prompt to model such functions by just symbolizing the return only, meaning that we would, in that case, we would just ignore the body of the functions. So we can do this with the global settings of model functions with ASM on. But there may be certain, functions that has inline assembly, but we still want them not to be modeled, right? Like, for instance, we don't want to model bar, although we know it has inline assembly. Then we can use this keyword or phrase, but use original with pattern, and then specify our pattern as bar. This is like any function that has bar in it, in its name, will not be modeled and will use the original definition. Yet, there may still be some functions that we want to model, although they have bar in their functions. And in that case, we can also use the except keyword and specify a comma-separated list of function names so that they would still be modeled. So if we apply this to our example, foo1 and bar1 would be modeled, meaning that their bodies will not be executed and their return value will be symbolized, whereas we will be using the original definition of bar. Now, we will have a problem because bar has an inline assembly. So KLEE normally doesn't handle inline assembly instructions. So we found a way to also abstract such instructions, and we have a setting. So if you say symbolize inline ASM on, what that means is that when the execution engine sees an assembly instruction, it will kind of ignore it. But if it has a return value, it will just symbolize the return value. So if we start with our entry point, the foo function, you see that we have a bunch of function calls. And if you remember that we model foo1 and bar1, then, and that we are symbolizing their return value, then y and w should have unconstrained values. So these if statements actually should hold true, and meaning that we can reach the assertion failure at L3 and at L9. Whereas since we're using the original definition of bar, and since bar returns a 0, obviously z will get 0, and then this if statement will evaluate to false, and we will not be able to reach this assertion failure. Okay, So if we go to global settings, model functions with ASM, we should see in the output 2 assertion failures, as you see. Okay, and if you open or look into these files, we will also see the specific line numbers. So on the slides, we simplify the code, but if you actually open the text files, these lines will make sense. Okay, so one way of modeling functions in prompt is symbolizing their return value. So if we have, let's say, external functions, they will definitely be modeled. The reason is that we don't have a function body to execute, right? We don't really have a choice. But the question is, if our external function, let's say bar in this example, has a pointer return type, then what do? We can set this null return on setting, and then in that case, any external function that returns a pointer type, a null value will also be considered for the return value. So in this example, let's say that, yes, foo is our entry point as usual, and we're calling bar, and we're storing the result in pointer y. So since on one of the paths, a null value will be considered for y, on this line L2, when we dereference this pointer, we should get a memory error. So if you can go to global settings directory and then null return directory and execute this, you should see 2 test cases generated and one being a pointer error due to the null return value. So this is about, again, function modeling. When we have, again, an external function, another thing that prompt does about the modeling of such function is that it havocs or symbolizes the arguments. This is just to simulate some type of like the most abstract side effect that's happening inside the function body that we don't know. But there are cases that actually we can skip such havocing operations, and in the global settings, if we say skip havocing singletons on, and then if we define a type to be a singleton, meaning that there can only be at most one instance of this type within the component that we're analyzing, then we will get a different type of behavior. So if we go back to our example, so we have the struct A, and one of the parameters of external function bar is an A pointer. Another argument is a B pointer. But since we say A is a singleton, when prompt actually models this function, since A1's type is a singleton, it will not be havoked. And what that means is that any assignments we have made that are reachable from A1, like in this one, they will be preserved. Whereas this other argument, since it is not a singleton type, it will be symbolized or havoked. And so we will lose any type of assignments that have been made to B1. Okay, so what that means is that this if statement will evaluate to false because we have set this value to 5 already. And so we will not reach this assertion failure. Whereas since we havoked B1, because the type is not a singleton, and bar is an external function, so since it will be unconstrained due to havocing operation, this if statement will hold, and then we will reach this assertion failure at L7. So if we can go to the skip havocing singletons directory under global settings and execute this, then you should see this, that we have two paths generated, and one of them is an assertion failure. So now we can talk about the data modeling aspect of PROSE and how prompt interprets such models. Okay, so so we have here bar function, and foo is our entry point, and we have a struct type with a function pointer field f, and we can write what is called a bound constraint, as you see here. A bound constraint has some constraint inside the parentheses, and then we have the where clause that explains what each of the variables we use in the constraint mean. So for instance, we say bar equals x, and then we say bar is a function, and x is the third field of struct or type B. The field indices start from 0, so therefore this is corresponding to this F field. So we have seen before how to initialize function pointer fields to null, but now we see that we can actually initialize such a field to a specific function. And we also have another bound constraint that kind of makes the first argument of foo greater than 0 with this bound constraint. Again, argument indices start from 0. That's why this is referring to the first argument. So if you look at the foo function, which is taking an int argument and a b pointer. So if we first check if a is smaller than 0, but our model says that it actually should be greater than 0. So we shouldn't reach the assertion failure at L2. And since we have actually initialized the F field of struct B for any instance, and we had actually only one because of this argument, and then this F actually corresponds to the bar function. So it means that at this line, we shouldn't get any invalid function pointer error, and we should execute the body of function bar. And as you see, there's actually an unconditional assertion failure at L4. So, so we should get an assertion failure at this point. So if you can go to function pointer directory under data modeling, you should be able to reproduce this example. As you see, we have only actually one test case generated, and it's about an assertion failure. And it is interesting to see on the stack trace that actually this is happening inside the bar function. And if you remember, bar is not called explicitly inside the foo function, but it's just because of our API modeling. Another important type of data modeling is about embedding relationships between struct types. So here we have struct A that is embedding struct B. Now, just to explain why this type of modeling is important, let me show you a figure. In this figure, as you see that on the left-hand side, so we have one scenario, right? and on the right-hand side, we have the ideal scenario. So the left-hand side, when a pointer gets lazily initialized, and assuming that the pointer's base type is a struct B, we would just, create this object without the proper context. But if it turns out that actually the code that we're analyzing expects this object to be created as embedded inside struct A, we may have issues, but we may also not have issues. Let's understand when we may have an issue. Let's assume that our code uses a pointer to the base address of struct B type object to derive a pointer to the base address of a, struct A type object. For that, actually, what happens is that system code performs some pointer arithmetic that uses a negative offset. So if we just, created object B like this, not within the proper context, then we would just get a memory out of bounds error. And the worst thing is that this would actually be a false positive, and it may also prevent us from covering more code because of this memory error. Whereas if we realize this dependency between struct B and struct A, that this gets embedded in struct A, then we can just tell prompt this fact with type A embeds type B phrase, and then what will happen is that whenever a pointer gets lazily initialized and that pointer type is B, it actually gets created inside struct A object. And if the code goes ahead and tries to drive a pointer from the base address of the B object to, get a pointer to A object, we won't have any issues because this address will be a perfectly valid address. Okay, so going back to our example, what you see here is what is known as the container of macro. In the Linux kernel, this is used a lot. We have actually found around 5,000 uses of container of, and I think it is used more because other type of helper functions get defined in terms of container of. So it is very common in the Linux kernel. So in this small example that we have an argument of type B, but remember that B gets embedded in A. But since we're telling prompt that type A embeds type B, when this gets lazily initialized, the B object is actually embedded in an A object. So when we apply this macro and when we drive this pointer EP, which is an address to the base of A object, we get a valid pointer. Therefore, at L3, L5, and L6, when we dereference this pointer, we don't get any memory errors. So to reproduce this, please go to the embeds directory under data modeling. And you will see that we don't have any error path generated. And you can also inspect, the K queries related to these tests to see what they're about. These are the if statements that actually you have seen. Okay, so in bound constraints, one of the things we can do is we can refer to the size of an array type argument. We need to use, in the var clause, we need to use argsize keyword. So we have here in this example, A2 as a pointer that will be lazily initialized. So we will treat it as an array of certain size. Remember, the default size is 20. But since we specify here saying that 35 equals W, where W is the size of the argument, the second argument. So then, and since this is actually a simple equality, then it means that we lazily initialize this argument as an array of size 35, not 20, which is the default value. And so we can use 34 as a valid index and not get any memory errors at L1. So to reproduce this example, you can go to the arc size directory under data modeling, and then you also need to go to the constant index. As you see, we don't have any error paths generated. Now, one thing I want to, get your attention to is if you look at the K-query for this test case, the constraint is actually, there's no constraint because we have an empty square brackets. And this is because when we specify the size, that gets actually embedded inside the memory representation, and we don't have any statement actually to refer to any symbolic value. Oops. Okay, so we can have a little bit more complicated stuff. Instead of a constant value, we may just have another symbolic value that gets equal to the size of the array argument. So for instance, x equals w, where x is whose first argument, and w is again the size of the second argument, which is an array. So since we define this relationship like this, then we can use this expression a minus 1 as an index, and we would not get actually any memory errors. To reproduce this, again, you need to go to the arc size directory, but this time to the variable index with simple equality. And if you look at the results, we get only one test case and no errors. Again, we don't have any path constraint because we didn't have any if statement. And even if we had if statements, as long as the if statements don't process any symbolic expression, again, we would not have anything in the path constraint. We may go further and specify even more complex constraints. For instance, in this case, foo has 3 arguments, and the first 2 arguments, a and b, we use them in the constraint as x and y, respectively. And we say x plus y is smaller than w, where w is the size of the third argument, which is an array. And also that x plus y is greater than 0. Once we define a and b this way, we can actually use a plus b minus 1 as a valid index. Again, no memory errors. Again, no if statement. So we should also not expect to see any constraint in the K-query file. So if you can go to variable index complex directory. Oh, now actually tracking back, normally apparently we shouldn't see any path constraint, I said, but actually I'm backtracking. Because if you look at it, we don't have any statement. However, since we provide the symbolic expression, actually what KLEE does is that it actually checks various possibilities of where this expression may refer to in the memory. And definitely it will be actually, as you see, so this, you see this addition operation of the arguments, and then this is actually compared against the size of the array and so on. So, and of course, we also mentioned that it would be greater than 0. So yeah, apologies, because we had this already expressions specified in the model, and that would be actually reflected in the path constraint. We can specify size constraints also on the array fields of structs. For instance, here we have a pointer field type E inside struct A. And when this object gets lazily initialized, and especially actually when we reference this field, which should be initially symbolic, because we have a argument A2 into foo, when it is time, or when we access it, for instance, here, when we access this field, it will get lazily initialized, and we say that size of this array should be 25. So we're kind of overwriting the default array size of 20 with the type-specific setting. We also have some constraint about the first and the second argument. We say that the first argument, which would be A, is greater than 24. And then the second argument, B, is actually equal to 24. And so if you look at these if statements carefully, we're actually, these actually should not hold, because they're just the reverse of these constraints. So we shouldn't reach the assertion failures at L2 and at L4. So the index B, which is the second argument that we use, since we initialize it to 24 here, should be a legal index, because size of B field inside the A struct is 25. But if we use A, which is declared as to be greater than 24, this should not be a legal index for this array. So we should get a memory error at L6. So if you can go to size of directory and then one level subdirectory, you can reproduce this example. And as you see, we have a, excuse me, we have a pointer error. Involving the first argument of function foo. Now, prompt can make sure that such constraints get applied to even embedded types. So, for instance, we have struct A here that, we have struct C here that embeds struct A. And if you look at it, all our constraints is like this one is about struct A. And if you look at this example, so there's actually there's a typo here, because this should be a C type. I apologize for this typo, but this argument is supposed to be a C type. So and then assuming that we're actually dereferencing the C2 field of such an argument, C type argument, then we will see that actually these constraints will be applied even to such objects. And so this is very similar to the previous example. We should not reach any of the assertion failures. And again, this should be a legal index, and this should actually create a memory error. So if you go to the two levels, constant size of example, under the size of directory, you will see the memory error generated due to memory out of bounds constraint. Okay, now let's look at some function modeling examples. Now, some functions may be regarded as memory allocation functions, and let's say that we want to ignore anything else that they perform, and say that we have this bar function that we want to leave it as an allocator, and let's say that actually the size of the memory is mentioned in the third argument. We can specify such functions with alloc keyword with the size argument telling us which argument is representing the size value. And then we can even tell whether we want to initialize the memory to false, initialize memory to 0 or symbolize it. So here in this example, we call bar, and then the third argument, its value is 10. It means that we'll be creating a memory chunk of size 10, and we will be returning the address as a return value, and that will be stored in pointer n. So if we use 9 as an index value into this array, it should be perfectly fine. But if we use 10, it will cause a memory error. So if you go to function modeling subdirectory and alloc modeling, you will be able to reproduce this error, which will be stored in this file, and it will give you the address that this. So as you see, it's a concrete address because we were using a concrete index. Another way of modeling allocation functions is designating one of the arguments as a destination for the address of the allocated memory. Like in this case, we want to say that bar creates some memory and it stores the address in D. And so we can do this again with the alloc keyword and use dest arg. So this says the fourth argument is the destination argument. And if we still want the function to return the address of the allocated memory, we can use mem return true. So in this example, although we actually pass 10 as a parameter, actually it's not going to be used as an argument or size argument. And the reason is this: in this mode of modeling, we use the base type of the destination argument as the size of the array. Since the base type is char in this example, it will be an array of size 1. And in this example, the address will be stored both in n, and it will be returned and stored in m. So we expect this assert statement to hold. And since it's an array of size 1, using index 0 is fine. Using index 1 will create a memory error. And if you can go to alloc with dest modeling directory under function modeling, you should be able to reproduce this and see the memory error reported in this file. We can also model the allocation functions with the free keyword, and we have to also mention the argument that is holding the address of the memory to be deallocated, like with the mem_arg keyword. So for instance, zot is defined as a deallocator, and we still define bar as an allocator with the arg size. So here bar creates a memory of size 10 bytes, returns the value and stores it in n, and then we pass n as the second argument, remember the index. So this will cause the memory to be deallocated, which is fine. But when we do the same thing at L5, this will lead to a double free, and we'll get a memory error. So if you go to free modeling directory under function modeling, you will see the pointer error generated, and you can inspect and look at the error. Okay, we can model a function by telling prompt just to symbolize its return value and ignore the arguments, meaning that don't have it the arguments, just symbolize the return value. In this example, let's say we model function bar, although we have a definition of function bar, right? So we call bar, So first we actually have this argument A that will be lazily initialized. And then we call bar, since it is return only, we will get the symbolic return value stored in Y, and nothing will happen to A. So what that means is, since it was just unconstrained before the memory pointed by A, it will still be unconstrained. And then we check whether it is not equal to 5. Remember that since we're modeling bar, its body will not be executed, right? So then it is, since this is unconstrained, actually this if statement will hold and we can reach the assertion failure here. Similarly, the return value will be symbolic and this will hold and we can reach L5. And you can go to return only directory under function modeling and reproduce this example. And you see the two assertion failures. All right. So in this example, we're kind of combining multiple specifications and we're trying to explain the side effect. So as you see, we define bar as return only. And I just said that, you know, when we have return only, the arguments are not havoc. But we can still ask prompt to havoc its arguments using havoc args specification by providing a comma separated list of argument indices that we want to be havoced. Also, we can overwrite some setting about singletons. Remember, we can turn on skipping of havocing singletons on, right? And then if we have a type like A that is singleton, as in the case of Zot, and we can say that, you know, although A is singleton and we're skipping havocing of singletons, please go ahead and still havoc the argument of Zot. And so we can enforce this symbolizing operation. So in this example, we first initialize our lazily initialized memory objects with some constant value. And then to show you that, you know, these settings take effect, like this D gets symbolized, A and C gets symbolized. However, B is not symbolized because bar is return only and we didn't specify the second argument. So we only specified the first and the third. So accordingly, because of havocing actually, you know, destroys all the assignments that we have done, only the assignment made for B gets preserved. So we should, yeah, because it is 5, we shouldn't reach this assertion, whereas we will be reaching assertions at L5, L9, and L11. So you can see 3 different assertion bug reports under this directory, which is called havoc args. Now, if none of the modeling approaches that we discussed so far work for your case, then what you can do is you can implement a model function. Let's say in here, Zot is our model function. And we say that Zot is going to model bar by saying bar modeled by Zot. Now, inside foo function, when we call bar, then actually we will just replace it with Zot's implementation. And what this does is actually it sets the memory pointed by A to 5. So this if statement should not hold, and then we shouldn't reach the assertion failure at L3. So if you go to model by directory, you can see that we're not reaching that assertion failure. So far, we have seen a very simple way of life cycle, meaning just a single entry point. But we can actually just combine functions using sequential composition using a semicolon. So here we say that first execute function foo, then execute bar. But we have a condition actually. So inside the square bracket, this one means that this execution will continue with bar only if foo returns 1. So inside the foo function, if you look at it, only under certain conditions we return 1, which is if this A field is smaller than or equal to 0. So we can check this type of execution because inside the bar function, we say that if this thing is actually greater than 0, then we give an assertion failure. But since this is ensuring that when foo returns anything other than 1, the bar will not be executed, obviously we should not reach the assertion at L2, whereas we will be reaching the assertion failure at L4. So if we can go to 2 entries, custom success, and I apologize for the cycle because it should actually be life cycle, then you should see the, as you can see here, you can see the assertion failure. In this part, we're going to talk about some real-world case studies. We have 3 memory vulnerabilities that we're going to introduce, and we were able to reproduce these with prompt. The first one is the heartbleed vulnerability. That's a memory out-of-bounds read that, when exploited, can leak secret data such as private keys. And you can find all the related files under case studies, the OpenSSL heartbleed directories. So our model actually for this example is very simple. So we specify the entry point as TLS1 process heartbeat, which is the function that hosts the vulnerability. It is actually manifested at this highlighted memcopy line. So what happens is that the size of the copying operation, the payload, is unconstrained, and it is actually controlled by the attacker. And so it goes over the source array. So we here choose initialization of function pointers to null. And this is because of this if statement. There is a message callback that gets executed if it is set, but the callback is actually not relevant to the vulnerability we are reproducing. So by doing this global setting, we can just avoid execution of this if statement body. And we also set the array size to 2 so that we have the necessary difference between the size of BP and PL to reproduce the error. If you don't set this, and I think it may be the case in your virtual machine instance, then you will still get the error reported for this memcopy as a memory out of bounds. Right, I think in that case. So, so here's the VM setting that shows how we reproduce this bug. And if you see, it's actually, it takes like 1 minute to reproduce it almost. So it is this particular test case that you should look at. And if you look at more carefully, this out of bounds read is really actually about the source address. The second vulnerability is one of the family of Blueborn vulnerabilities. So this is inside the Bluetooth protocol stack implementation for the Linux kernel. And so you can find the relevant files under the JSC benchmarks, BlueZ, and L2cap config RSP directory. So what happens is that, so this bug gets manifested when the attacker talks about an unbounded size of configuration options. Since the response buffer, which is buff in this case, has a specific size 64, and if the attacker tries to go beyond this size, as the size of this buffer is actually not checked with inside this while loop that goes through every configuration option, parses it, and then writes to the response buffer. This may lead to a memory out of bounds write that can be exploited with a remote code execution. So the model is a little bit longer. So let me see. I think I'm going to talk about this particular setting that says type L2 caption embeds type list head. So this is list head is a generic linked list implementation in the Linux kernel, and for this component that we analyze, if we don't specify this, then as I mentioned before, the pointer that would be derived to point to the L2 caption object would lead to a memory error, and it would be a false positive, and it would actually prevent us from making progress beyond this point. So with this setting, we were able to actually make progress and reproduce the error. The other type of things are like setting some of the callback functions and modeling some allocation and deallocation functions, certain functions like logging functions as return only. And we also implemented a model function for this particular function. In the original one, there is a switch statement, and this function gets actually executed inside the while loop, and that causes actually a path explosion. So instead of doing that, we modeled this function and chose a specific configuration option and set the size accordingly, and then we were able to reproduce the error much faster. So even in that case, as you see, the bug report is actually on test 69. So it may take around 7 minutes to reproduce on a virtual machine. And this is the stack trace and the line number and also the assembly line number for this particular bug. So our results, the timing results we report here is actually on a rack server, but as I mentioned, it may take a little bit longer on your virtual machine. The third real-world vulnerability is a use after free in the USB TV driver from the Linux kernel. This is also available under JSC benchmarks. So if you go to drivers, media, USB TV, you can have access to these. We actually analyzed something like 57 drivers from the Linux kernel, and we have also drivers from the sound and network subsystem, but I'm just going to talk about this one here. So this function actually gets manifested inside the probe function. What happens is that after the driver registers itself with your video subsystem, it registers itself with your audio subsystem. But when this fails, actually, it goes to some cleanup code, and it first tries to deregister itself from the video subsystem. And this leads to the allocation of the custom data structure through some callback. So it is in a way implicit. And then, although this data structure actually gets deallocated here, it gets accessed. And then this causes a use after free, and after that, actually, the custom data structure gets deallocated explicitly, causing a double free. So in the model, we have some singleton types specified, allocation, deallocation functions, and some model functions for the video subsystem. Since this bug actually involved reference counting mechanism, we had to model the relevant API functions, and you can find all those function source code as well as the bit code in the respective directory. So here the lifecycle model actually uses sequential composition of the probe function and the disconnect function, but actually the bug can be reproduced if you just use USB TV probe as an entry point. And this actually is also recovered very fast. And here, this A66 is actually the line number in the assembly file. In this particular example, we didn't, I guess, use -G, so we cannot see the source line number. But I would like to take this opportunity to show you that you can actually, and you should get used to analyzing LLVM IR and make sense of the reported bugs. So if you go to this line and open assembly.ll file under KLEE last directory, you'll see that this line number is corresponding to this load instruction. So we're trying to load from an address, but the thing is that this is the address of the memory object that get already deallocated. And as you see, it's not a surprise that this is going to be passed to USB put dev. So if you try to relate it to the source code, yes, we're exactly getting a use after free at this line. So I hope that actually you can apply prompt to your own components. Unfortunately, we don't have time to do an interactive session about that, although I wished we could do that. So first recommendation is install prompt on a high-end computer. Obviously, virtual machine is good for the pedagogical examples, but you want to use the high-end server for your real component. And you will need to generate the bitcode for your project. There are nice tools like whole LLVM that uses the build system, like you make files. You can easily incorporate that and then create the bitcode easily. But in certain cases, you may still need to link the generated bitcodes. For instance, when we're analyzing OpenSSL, we have to create bitcode separately for the crypto library and the SSL library, and then we have to link them together. When you start modeling, please start with a simple model, and based on your goal, whether it is about bug finding or achieving certain amount of coverage, then detail your model as needed. And I wish you a happy modeling and bug hunting. We would like to thank the National Science Foundation and Semiconductor Research Corporation for funding this project. And we would like to thank our undergraduate researcher, Joshua Nelson, for working on the parser. And if you use prompt, again, please cite our paper. And thank you for your attention. If you have any questions, I'll be happy to help.